Hello everyone and welcome to the online lecture for college algebra. In this video we're going to cover section 1.2 on constructing models to solve problems. So for the first type of problem in this section, we're not really building models or anything like that yet. We're simply introducing the concept of a formula, which is just an equation involving two or more variables, usually for some kind of meaningful relationship in the real world. And we're going to be rearranging the formulas to suit our needs, so solving for a specific variable in the formula. So for example, the formula I have listed here on the slide is a formula for converting degrees in Fahrenheit into degrees in Celsius. So you have a certain temperature in Fahrenheit, you subtract 32 from it, then you multiply it by 5/9, and that will give you the temperature in Celsius. But let's say you wanted to convert in the opposite direction. You wanted a formula instead to go from Celsius to Fahrenheit. Well, all we have to do is solve this same formula for F. So in this case, I would want to get rid of this 5/9 first. So I could divide both sides by 5/9, but dividing by a fraction is the same as multiplying by its reciprocal. So that would be the same as 9/5 times C. And then if I wanted to solve for F, I would just have to add 32 to both sides. So we would get the formula degrees in Fahrenheit is equal to 9/5 degrees in Celsius plus 32. And this is incredibly useful in mathematics in general. Anytime you have a formula relating to or more variables, people get hung up on the idea that it's built specifically to solve for one of the unknowns, when that's not the case. You can always just rearrange the formula to suit whatever variable you're looking for at the given time. So let's take a look at a few more examples of varying difficulty. In example 1, we're asked to solve the following formulas for the specified variable. This example starts off pretty straightforward with part A. We get V is equal to L times W times H. This is actually the formula for volume of a box, length times width times height. And we are asked to solve this for W. Well, this one's pretty straightforward because it's just straight multiplication and division. There's no addition or subtraction getting in the way. So if I want to get the W by itself, all I have to do is divide by L times H. And we get the formula W is equal to V divided by length times height. Part B is a little bit trickier because our variables are in denominators now. So think about what type of equation this is based off what we were doing in section 1.1, and think about what you would do to solve that type of equation. So try pausing the video here and see if you can find the solution to part B for example 1. So this is a rational equation. We've got variables in denominators in this case. So what we can do is multiply everything by the least common denominator. So we've got 1 over P is equal to 1 over Q plus 1 over R. None of these denominators have anything in common with each other, so our least common denominator is just PQR, the product of the three. So I'm going to multiply both sides of the equation by PQR. And then on the right-hand side, distribute through. On the left-hand side, the p's cancel, so we're just left with QR. On the right-hand side, in the first term, the q's cancel, so we're left with PR, and in the second term, the r's cancel, so we're left with PQ. Now, that's a lot of the work, but we're not quite there yet, because we're still trying to solve this for R, and you notice that we have two of those right now, which makes this a little bit trickier. Well, there's a common trick that we use in algebra to help out with situations like this. Anytime you have a variable to the same power in multiple locations, you pretty much need to use the greatest common factor method to isolate the variable. So, for example, let's say you had 2x plus 3x. You guys know that you could combine those together, add like terms to get 5x. But let's say for a second you didn't know what 2 plus 3 was. So you didn't know how to combine those coefficients together. What you could instead do is factor the x in common out between the two terms. That's still 5x. This is the same result. The only difference is that we didn't combine these together because we didn't know what it was. But what we did was we took two x's, and by factoring, we turned it into a single x, which is much easier to solve for. And so that's what you want to do with the r's here. I'm going to group up both r's on the same side. So I'm going to subtract the PR over to the left. So it's going to be QR minus PR is equal to still a positive PQ. Then I'm going to factor out the R in common on those two left terms, which would give us Q minus P left over. And now this is just a product, R times this parentheses. So if I want to isolate R, I can divide this entire parenthesis across to the other side. And so our final answer here, R is equal to PQ divided by Q minus P. To get a little bit more practice with this trick of factoring out the variable in common to isolate, try pausing the video here and see if you can find the solution to part C of example 1. So we're asked to isolate x in this formula, and it's the same idea as we had in part B. The trick is to group up all the terms with x next to each other and factor it out. So we've got our xz squared plus xw squared. I'm going to subtract the xy squared across to the other side. Still be equal to positive 5. And then I'm going to factor out the x in common between all three of these terms, which would just leave us with z squared plus w squared minus y squared. And then last but not least, I'm going to once again just divide that entire parenthesis across to the other side. So our final formula here is x is equal to 5 divided by everything in this parentheses, z squared plus w squared minus y squared. I really want you to make an effort to remember this idea of grouping up terms and factoring out the common variable, because that's going to be something that comes up a couple more times throughout the course and is really useful for solving certain types of equations. So now let's get into the actual modeling portion of the section. And all told, we're going to be dealing with 3 different types of word problems in this section. The first of those 3 types are called geometric problems. And they're called that because these are word problems involving formulas from geometry, like perimeter or area, or if you're dealing with a circle, circumference. Even if you were dealing with 3-dimensional shapes, you could have volume, right? Anything that pertains to geometry, more or less. The idea is that for this type of problem, you usually want to try to draw a diagram so that you can figure out what shape you're dealing with, because it's not always just given to you obviously in the problem. And then once you figure that out, you want to write a formula that involves the thing you're trying to solve for, the thing the question is asking you to find, but you need to be careful to write it in terms of a single variable so that we can solve for it. Once you've solved for the unknown, you want to be careful, make sure you reread the problem carefully and figure out what exactly they're asking for, and make sure you actually answer the question. It's a common failing of students with word problems that they get to a number, they put a box around the number and call it a day, even if that number doesn't necessarily answer the question that is being asked of them. So be careful. Make sure you actually interpret your results and answer the question. So let's take a look at a couple of geometric problem examples. Here in example 2, we're told that a frame maker made a large rectangular frame using 10 feet of molding. If the length of the finished frame was 2 feet more than the width, then what were the dimensions of the frame? So in other words, what's the length and width of the finished frame? All right, so as far as the picture goes, we're dealing with a rectangular picture frame. The 2 dimensions that we're interested in here are length and width. And if you labeled them in the reverse order, that would be fine. And we know a couple things here. First is that we know a relationship between length and width. So we can write it in terms of a single variable. So let's say for a second that I call the width x. That's what I want to try to solve for. We know the length is 2 feet more than the width. So it would be width plus 2, or x plus 2. Now, it's not the only way you could have set up this problem. If you called the length x, then since it's 2 feet longer, or 2 feet longer, width would have been x minus 2 in that case. Either way, it would get you to the same answer regardless. Now, we do know one other piece of information here, and that is the fact that we know they were using 10 feet of molding. That is the perimeter of the frame, right? The molding is what goes around on the outside. And so we know that the perimeter is just the sum of the sides. So it would be 2 widths plus 2 lengths, and that has to be equal to 10 feet. And so now we can write it all in terms of a single variable. Because w is x, that would be 2x. And be a little bit careful here. Because length is x plus 2, this would be 2 times all of x plus 2 is equal to 10. And so now we can solve for x. I'm just going to distribute that 2 through. Be careful, that's 4 now, 2 times 2. I'm going to combine like terms. 2x plus 2x is 4x. Subtract this 4 from the other side. 10 minus 4 would give us 6. So x would be equal to 6 divided by 4, or if we reduce, 3/2. So let's turn this into a decimal to make the next part a little bit easier. If x is 1.5, again, don't just put a box around that and say you're done. You haven't answered the question yet. They were asking for the dimensions of the frame, length and width. So we need to answer that. The width was just x. So width in this case would be 1.5 feet, because that's what our x is. Length was 2 feet longer than that, 1.5 plus 2, so it would be 3.5 feet. Let's take a look at one more geometric problem with example 3. We're told that Jen owns a 4-sided lot that lies between 2 parallel streets. If her lot, which is 90,000 square feet, has 500 feet of frontage on one street and 300 feet of frontage on the other, we're asked how far apart are the streets. So this is a good example where drawing a diagram can really help. So we've got 2 parallel streets. So they're traveling in the same direction, but not overlapping with each other. And then we've got a lot in between, and this lot has 300 feet of frontage on one street, so that's basically the border of the lot and the street, and 500 feet of frontage on the other street. We want to know the distance between the two. Now this shape that we ended up creating has a name. We call it a trapezoid. So you can bet that we're going to need some kind of formula related to trapezoids. And because they gave us the area of the lot, it's probably a good idea to look at the formula for area of a trapezoid. Now this is not one that I'll expect you to remember on a test. As long as you remember perimeter and area of squares and rectangles, that'll be good enough. I'll give you any other formulas that you might need. But the idea behind area of a trapezoid is pretty straightforward once you understand it. The idea is that we find the average length of the bases. So you do base 1 plus base 2 divided by 2. You average the two, and then it becomes just area of a rectangle, where it's length times width, but in this case, we instead say base times height. So you take your average length of the bases and you multiply it by the height. And so that's what we're working with area of a trapezoid. Also sometimes written instead like this, which is just a rearrangement of the terms that we have here. So let's see. Our area, the area itself over here on the left-hand side, we know is 90,000 from the problem. The height of the trapezoid is actually what we're looking for in this problem. That's the distance between the two streets. And then it doesn't matter which frontage you label as base 1 and base 2. You'll get the same results either way. So we're going to do half base 1 plus base 2, so 500 plus 300. And this is times h, which is the variable we're trying to solve for. So let's simplify a little bit. The 500 plus 300 would give us 800, but then we would multiply it by 1/2. So this is 400h. And if we want to solve for h, we just divide both sides of the equation by 400. Now, let's pay attention to the units here. And you can probably just figure out the units based off what we're working with in the problem. We've got feet of frontage, and the area is in square feet. So everything's consistent here, which is important. We need it to all be in terms of the same unit. But you can also see that work out in the problem as well. The area, the 90,000 here, is square feet, whereas the 400 in the bottom, because it's the average length of the bases, these are both in feet, is just feet to the first power. And then just like x squared over x would reduce, the same actually holds true for units as well. The feet would reduce, and so we just get feet. Makes sense that this length is measured in feet, just like the bases on top and bottom. And so now I'm just going to plug this into a calculator. 90,000 divided by 400, and that would give us a total of 225 feet. All right, this actually answers the question, so I'm okay putting a box around this. This is the distance between streets. The second type of word problem we're going to look at in this section are called mixture problems. And they're exactly that. They involve creating a mixture from two or more things and then determining some quantity, percentage, price, other things of the resulting mixture. And so the setup is usually going to go something like this. We're going to have usually two, but you could have more and it would be the same thing, objects that we're mixing together. They might be liquids, they might not be. So we've got solution 1, we've got solution 2, and when we add these together, we're going to get the final mixture. Let me take a specific example in order for us to work through this. Let's say you were dealing with, say in the next example, we're going to be working with butter, fat, and milk. So like 2% milk, 5% milk, 1% milk, so on and so forth. Then one of these, the top row in these beakers, is going to represent just the pure amount of fluid or the amount of solution. And then I'm going to do a second row in these beakers that's going to represent the percentage of some quantity. In our next example, it's going to be the percentage of butterfat, but it could be percentage of all kinds of things. That's also where you would put the price if you were instead working with a price mixture problem, so on and so forth. And so let me put some fake variables here for a second. The amount of solution is A, the percent of some quality is X. Then let's say for a second we're talking about amount of milk and percent of butterfat If we multiply those two together, that would give us total butterfat. The total amount of whatever we're interested in each solution. And so we're going to do that for each of the beakers, do a product going down, and then it'll be these things at the bottom of each beaker that we're going to end up using to set up our equation that we solve for our variable. All right, so let's actually take a look at this through an example. So in example 4, we're asked how many gallons of milk containing 5% butterfat must be mixed with 90 gallons of 1% milk to obtain 2% milk. So we're taking a very diluted 1% milk, we're mixing it with a 5% milk, and we want to end up somewhere in between at 2%. So let's think about what we're working with here. We're adding two things together. In this case, the two solutions we're adding together is 1% milk and 5% milk. What we hope to get out of that, the final mixture, is 2% milk. In the top row, I'm just going to put amount of milk. And keep in mind that your variable is going to show up in here somewhere. For 1% milk, we know we have 90 gallons. For the amount of 5% milk, that's what we're asked to solve for in this case. How many gallons of 5% milk do we need? So that's actually where our x is going to be in this problem. And then for the 2% milk, it's always just the sum of the previous two, right? You're taking 90 gallons, you're adding x more gallons to it, so you're going to end up with 90 plus x gallons of milk when all is said and done. All right, so that's the amount of milk. Next, we're going to have the percent of butterfat. And that's just in the name of the milk. So that's pretty straightforward. We've got 1% milk, we got 5% milk, we got 2% milk. Now you could write these as decimals to represent the percentages, but truth be told, you can just use the raw numbers as well, because it would be like multiplying both sides of the equation by 100, which would keep it balanced. So there's no need to introduce extra decimals into the mix. Right? And so now we multiply going down. So for the 1% milk, we've got 90 times 1. For the 5% milk, we've got 5 times x. And for our final 2% milk, we multiply those two together. We've got 2 times all of 90 plus x. And so this is now the equation that we will use to solve for x. I'm going to simplify this a little bit. We've got 90 plus 5x is equal to, if I distribute the 2 through, 180 plus 2x. And now this is just a linear equation. So I'm going to subtract 2x from both sides to get a 3x over on the left. And if I subtract 90 from both sides, that would give me a 90 over on the right. So it's just about rearranging the terms here. Then I just divide both sides by 3. And so we get that x has to be equal to 30 gallons. It makes sense that you don't need as much of this as you had of the 1% milk, because you're not trying to end up exactly halfway in between. If you added 90 gallons of 1% and 90 gallons of 5%, you would end up halfway between 1% and 5%. But in total, we only wanted to bring it up to 2%, so we didn't need as much of the 5% milk in this case. So let's take a look at another one. In example 5, we're told that a mechanic is working on a car with a 20-quart radiator containing a 60% antifreeze solution. How much of the solution should he drain and then replace with pure water to get a solution that is 50% antifreeze? So this one is similar to example 4, but it's not exactly the same. It does have a little bit of a difference to it, but try pausing the video here and see if you can find the answer to example 5. All right, so just like in the last one, we're mixing two things together. To get a mixture, what we're mixing together this time is the 60% antifreeze that we're starting with and pure water. And what we want to end up with, our final solution, needs to be 50% antifreeze. So let's start with just amount of, not necessarily antifreeze, that'll be the final thing. This is just amount of antifreeze solution, the amount of liquid that we're working with. So this time around it's a little bit different because we know we want to end up ultimately with 20 quarts, the capacity of the radiator. What we want to know is how much should he drain and then replace with pure water. So there are a couple different ways you can arrange the variable here, but I'm going to call x the amount of pure water that we add in. That means that we need to figure out what this amount of 60% antifreeze needs to be in our formula. It's not 20 plus x in this case because remember, this plus this has to be equal to this. So let's set up a dummy variable for a second so I can show you why this works the way it does. So let's call this a. If a plus x has to add up to the total capacity of 20, then what would a be in terms of x? If you just subtract x from both sides, a would have to be 20 minus x. It is the 20 quarts that you started with minus the amount that you drained to replace with water. All right, these two still have to add up to give you the amount in the final solution. The only difference is that we started off by knowing the amount of our final solution this time around. That's really only the big twist of this problem. Everything from here on out will play out pretty much exactly the way it did in example 4. For percent of antifreeze, for 60% is 60. For water, it's 0% antifreeze, hopefully. And for our final amount, we want 50% antifreeze. And so then we multiply going down. So we've got 60 times 20 minus x plus 0 times x, so that's going to go away completely, is equal to 20 times 50. So if I distribute this through, 60 times 20 would give us 1,200 minus 60x. Remember to multiply both parts by 60. And this is going to be equal to 20 times 50, which is 1,000. So if I subtract 1,200 from both sides, we would get a negative 60x is equal to a negative 200. Divide both sides by negative 60. Negative divided by a negative becomes a positive. And then if I just reduce this a little bit, this would be 20 over 6, which if we divide both the top and bottom by 2, would reduce to 10/3. So 10/3, and the units we're working with here are quarts. That would be about 3 1/3, so 3.3 repeating quarts. So let's take a look at one more mixture problem. This time, instead of dealing with percentages in a solution, we're dealing with dollar amounts, but it's going to work pretty much the same way when all is said and done. So in example 6, we're told that raisins sell for $4.50 a pound. bran flakes sell for $2.80 a pound, we're asked how many pounds of raisins should be mixed with 12 pounds of bran flakes to get a final mixture of the two that sells for $3.14 a pound. All right, so let's see what we got. This time, we're taking raisins, we're adding bran flakes to end up with a mix of the two. Let's start with just the amount that we're dealing with, the quantity. So let's see, we have this 12 pounds here, that's of bran flakes. So we got 12 pounds of bran flakes. As far as the amount of raisins we have, how many pounds of raisins, that's our unknown in this case. So an X amount of raisins, which means our final mix will be 12 plus X pounds. In the second row this time, we don't have a percentage, but now we're going to do price per pound. So for raisins, we've got $4.50. Bran flakes, we've got $2.80. And for our final mix, we're looking for $3.14. Then if we multiply going down, if our amount is measured in pounds and we multiply this by the dollar amount per pound, then the pounds basically reduce each other away. The bottom row is going to represent total cost of each. All right, so you got $4.50 a pound times X pounds for raisins, $2.80 a pound times 12 pounds for bran flakes, $3.14 a pound times 12 plus X pounds for the mixture. And so now we have our equation that we solve for X. We've got 4.5X. I'm going to go ahead and multiply these two together with a calculator. 2.8 times 12, which would give me 33.6. And this is going to be equal to, I'm going to distribute this through. So it's going to be 3.14 times 12 plus 3.14 times X. But the reason I'm writing this out to the side is I'm going to go ahead and plug this into a calculator. So 3.14 times 12 would give me 3768 plus 3.14x. Now it's just about combining like terms, solving the linear equation. So I'm going to move my x's over to the left. This is going to be a 4.5x. I'm going to subtract 3.14x from both sides to move it to the left. And this is going to be equal to my constants, 37.68. And then I'm going to subtract 33.6 from both sides to move it to the right. And now I'm going to combine like terms. So I'm going to use a calculator to help me out with both of these. And I get 1.36x is equal to 4.08. And last but not least, in order to solve for x, I just need to divide that coefficient across to the other side. And I get 4.08 divided by 1.36, which happens to work out nicely in this case. That's not always going to happen, but it happens to give us exactly 3 pounds. If this did give us some kind of decimal, in this case it would be wise to just round to 2 decimal places because you're working with money. And it doesn't make sense to go out further than a penny. This brings us to our final type of word problem of this section, and these are work problems. And so work problems are whenever 2 people or machines are working together, or sometimes they could even be working against each other to accomplish a task. So as a base example, suppose two people are painting a house at different rates. Joe and Frank are painting a house for 2 hours and they finish the job, we're assuming, in that time. We're told that Joe paints at a rate of 1/6 of the house per hour, while Frank paints at a rate of 1/3 of the house per hour. Then you can find the amount of the job they finish by multiplying their rate times time. So for, let's see, the one that was doing 1/6 was Joe. He did 1/6 of the house per hour times 2 hours. That would give you 2/6, which would reduce to 1/3. So he painted in total 1/3 of the house. And then Frank was doing 1/3 of the house per hour for 2 hours. So he ended up painting 2/3 of the house. So this is the foundation for how we're going to work these problems. There's two key things to take away from this. The first is that the rate times time gives you the portion of the job completed, or as a formula, work completed is equal to rate times time. Now, in this case, they straight up gave us the rates. In most of our problems, we're going to have to find the rates. And we'll talk about how to do that in the next example that we're going to work. And then the other key thing to take away here is that in the previous problems, the mixture problems, we were taking the total amount of whatever we were working with, dollars or antifreeze or butterfat, and we were adding them up to get the final amount. So we had to know what the amount of the final one is. In the case of work problems, we're going to assume that they're finishing the job, so the total amount of work, the sum of work completed, is always going to be equal to 1. Together, they painted the one house that they were looking to paint. Right? So rate times time gives their portion of the job completed. The sum of the work done should always be equal to 1. So let's take a look at an example, and we'll arrange this data in a table similar to the way we were kind of using the beakers for the mixture solutions before. So in example, we're told that Leah can trim the hedges around her property in 8 hours using an electric hedge trimmer. Ryan can do the same job in 15 hours, almost twice as long, by using a manual trimmer. The question is, if they both work at it, Leah with her electric trimmer and Ryan with his manual trimmer, how long would it take them working together to complete the job? And you should be able to kind of ballpark this by looking at it, not necessarily accurately, but if Leah can do it in 8 hours by herself, then if she has Ryan helping her, you should assume that the final time should be less than 8 hours. He shouldn't be making her take longer than if she were working by herself. So I'm going to do a table here to collect our information. And this is basically going to be a sideways version of the beakers that we were looking at earlier. So I'm going to have a row for Leah. I'm going to have a row for Ryan. And then I've got 3 pieces of information. We've got rate, time, and then their portion of the job completed, which I'm going to call work, which is just the product of the other two, rate times time. And keep in mind your variable is going to show up in here somewhere. All right, so let's talk about how to find rate. The idea is that if it takes her 8 hours to complete the job by herself, then you always just put that under 1. She completes 1/8 of the job per hour. So her rate is going to be 1/8, right? Because if she was doing 1/8 the job per hour times 8 hours, rate times time, she would complete the entire job in that time. So it's always just the reciprocal of the time to complete the job solo. Similar then for Ryan, if he completes the job in 15 hours alone, he is completing 1/15 of the job per hour. So his rate is going to be 1/15. The time is actually not their time individually. Be careful, that's an easy mistake to make. This time represents when they're working together. And that's actually what we're trying to find here. How long does it take them to complete the job if they're working together? In this case, it's X for both because they're starting the job at the same time and they're finishing the job at the same time. If one of these were offset, we would account for that in the variables. So for example, if we were told that Ryan started working 4 hours later, then his time would be X minus 4. He worked 4 fewer hours. But in this problem, they're just working together from beginning to end. So their times are both X, which is what we're trying to solve for. Then Leia's total work done is 1/8 times X, or you could write that as X over 8. Ryan's work done is 1/15 times X, or X over 15. And if you add their work together, it's always equal to job completed, 1. So this is the equation that we want to solve for X. Right, so this is going to take a little bit of work. This is a rational equation because we've got fractions in the mix, so we're going to find the common denominator and multiply it through. 8 and 15 don't have any factors in common. 15 is 5 times 3, whereas 8 is 4 times 2, or 2 cubed. So there's no overlap between the two, which means the common denominator is just 8 times 15. And truth be told, you could always just multiply them together in this case because you don't necessarily need the least common denominator. Any common denominator will work here. The least common denominator just prevents you from having to do reducing at the end. So 8 times 15, the product of the two, is going to give us 120. So I'm actually going to leave it as 8 times 15 on the left and the right because it's going to make my multiplication a little bit easier. So if I distribute that through, in the first term, the 8's will cancel. So that would leave me with 15x. In the second term, the 15's will cancel. So that would leave me with 8x. And on the right-hand side, we just get the 8 times 15, which is the 120. So now we can solve for x. 15 plus 8 would give us 23x. Divide by the 23. And if we plug this into a calculator, we would get that this is about equal to 5.2 hours. Definitely less than the 8 that Leia could do the job on her own in. Let's take a look at one more example of a work problem. In example 8, we're told that with an old combine, Nikita's entire wheat crop can be harvested in 72 hours, but with a newer one, the job can be done in 48 hours instead. We're asked how many hours would it take to harvest all of the wheat if both combines work together, but the new combine isn't used for the first 6 hours. Maybe it's unavailable. So this is an example of one with a time lag. So let's set up our table and see what we're working with here. So once again, I'm going to have 2 rows in this thing. We're going to have the old combine and the new combine. We need rate, we need time, and we need the product of the two for our final equation. So let's start with the rates. And the time lag does not come into play for this. This is just their rate per hour for the job. So if the old combine can do the job solo in 72 hours, its rate is 1 over 72 of the job per hour. And if the new combine can do the job in 48 hours, its rate is 1 over 48 of the job per hour. Now the time that they're working on this job together is where the time lag comes into play. So if I use X for the amount of time that the old combine is working, then since the new combine isn't used for the first 6 hours, it's working 6 hours less time, so its time will be X minus 6. Now you could instead flip this, but you would have to be careful if you did. If you called the new combine's time X, then the old ones would be X plus 6 more hours. But if that's the case, this is your final answer for the problem, right? Because it's the total amount of time to complete the job. So we're assuming that we're starting from when the job is started, which is just with the old combine. So now we can multiply them together. So for W, we've got X over 72, X times 1/72. And for the new, I'm going to leave this as 1 over 48 times X minus 6. If we add those two up, X over 72 plus 1 over 48 X minus 6, this should be equal to job completed, equal to 1. All right, and so these are often rational equations because of the fact that their rate is a reciprocal like this. And so once again, we need to find a common denominator and multiply that through the equation. So this one's a little bit trickier because the numbers are larger here, but let's treat it the same way we would variables back in section P6. So the largest number that would divide into both of these would be 24, because 72 is 24 times 3, and 48 is 24 times 2. So our least common denominator then will be each factor that shows up. So in this case, we've got a 24 times a 3 times a 2, or 24 times 6, which would give us 144. You can double check this pretty easily. You should make sure that both 72 and 48 divide cleanly into 144. Otherwise, our fractions won't reduce properly. And in this case, it does, so we're fine. So I'm going to multiply both sides of this equation by 144, distribute it through. So on the left, we get 144 x over 72 plus 144 over 48 times x minus 6 is equal to 144, and now I'll reduce. The 72 will divide into the 144 to give us 2, still with the x. 48 will divide into 144 to give us 3, but this is still times x minus 6 in parentheses, equal to 144. So now I'm going to distribute through. To get 2x plus 3x minus 18 is equal to 144. And now I'm going to move over here to give myself a bit more space. If I combine the two x's, that gives us 5x. I'm going to add 18 to both sides to move that across, which would give me 162. And then last but not least, I just need to divide both sides by 5, which would give me 32.4, and these are in units of hours. You should always ask yourself if your answer is reasonable based off the problem. The old one would have done it in 72 hours. The new one would have done it in 48 hours alone. So even though the new one wasn't used for the first 6 hours, it makes sense that together they would still be less amount of time overall than the 48. This seems like a reasonable answer. You can always double check your answer, of course, by plugging it back into the original equation that you set up for work. You could even, if you want to get fancy, plug X into the work done column to figure out what portion of the job each combine did. So if you did 32.4 divided by 72, that would give you 0.45. Even though it was working longer, the old combine ended up doing 45% of the job. Whereas if you plug it into the bottom one, 32.4 minus 6 divided by 48, that would give you 0.55. So the new combine ended up doing 55% of the total job. All right, and so that is it for section 1.2. A lot of students find this one of the trickier sections in chapter 1, mainly just because word problems in general tend to give people trouble. But in terms of types of problems to expect from this section, there are just 4 in total. Solving a formula for a given variable, that's for the most part just straight up algebra, just with letters instead of numbers. And then you've got the 3 types of word problems. Geometric problems, which are mainly about drawing diagrams and using formulas from geometry. You've got mixture problems and work problems, both of which are about using diagrams or figures to kind of help you figure out what's going on, organizing your information effectively. As always, if you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.